Science has finally solved mystery about the moon that's puzzled scientists for decades. It turns out that the moon's earliest history is written below the surface, and it just took the right combination of models and data to unveil that story. The moon turned itself inside out to form the cratered surface we see today, according to the scientists. Isn't that bizarre? Researchers combined computer simulations and data to show how oceans of magma sank and rose to the moon's surface again over billions of years to form its current shape. Astronomers say these magma oceans fluctuated over thousands of years due to gravitational instability. The American research team say their findings could offer important insights into the evolution of our moon and even potentially for planets such as Earth and Mars. Around 4.5 billion years ago, a small planet smashed into our own young planet, flinging molten rock into space. And over the preceding millennia, the resulting debris slowly combined, cooling and solidifying, forming our moon. However, the details of how this process occurred have thus far remained heavily debated by astronomers. Most of our knowledge on the origins of the moon comes from analysis of rock samples collected by Apollo astronauts over 50 years ago, combined with theoretical models. Samples of basilic lava rocks showed surprisingly high concentrations of titanium, whilst other satellite observations found that these titanium-rich volcanic rocks are primarily located on the moon's near side. Near us, that is. But how and why they got there has remained a mystery until now. As the moon formed fast and hot, it was likely covered by a global magma ocean, and as the molten rock gradually cooled and solidified, it formed the moon's mantle and the bright crust we see when we look up at the moon, full moon at night. But deeper below the surface, the younger moon was wildly out of equilibrium. Models suggest that the last dregs of the magma ocean crystallized into dense minerals including ilmenite, a mineral containing titanium and iron. Weiguan Liang, who led the research, was part of his doctorate work at the University of Arizona Lunar and Planetary Laboratory, LPL, explained because these heavy minerals are denser than the mantle underneath, it creates a gravitational instability, and you would expect this layer to sink deeper into the moon's interior. In the millennia that followed, that dense material sank into the interior, mixed with the mantle, then melted and returned to the surface as the titanium-rich lava flows that we see on the surface today. Our moon literally turned itself inside out, co-author Dr. Jeff Andrews Hanna, an associate professor at LPL, said. He said, but there has been little physical evidence to shed light on the exact sequence of events during this critical phase of lunar history, and there's a lot of disagreement in the details of what went down literally. On the many possibilities, such as whether this material gradually sank or did so all at once after the moon fully solidified, Dr. Adrian Bouquet of the German Aerospace Center in Berlin said, without evidence, you can pick your favorite model. Each model holds profound implications for the geological evolution of our moon. In a previous study from Peking University, Beijing, models predicted that the dense layer of titanium-rich material beneath the crust first migrated to the near side of the moon, possibly triggered by a gigantic impact on the far side, and then sank into the interior in a network of sheet-like slabs, cascading into the lunar interior almost like waterfalls. But when that material sank, it left behind a small remnant in a geometric pattern of intersecting linear bodies of dense titanium-rich material beneath the crust. And when we saw those model predictions, it was like a light bulb went on, Dr. Andrew Hanna said, because we see the exact same pattern when we look at subtle variations in the moon's gravity field, revealing a network of dense material lurking below the crust. In the new study, the researchers compared simulations of a sinking ilmenite-rich layer to a set of linear gravity anomalies detected by NASA's GRAIL mission, whose 2 spacecraft orbited the moon between 2011 and 12, measuring tiny variations in its gravitational pull. These linear anomalies surround a vast dark region of the lunar near side covered by volcanic flows known as mare, the Latin word for sea. The team found the gravity signatures measured by the GRAIL mission are consistent with ilmenite layer simulations, and that the gravity field can be used to map out the distribution of the ilmenite remnants left after the sinking of the majority of the dense layer. Liang said, "Our analysis showed that the models and data are telling one remarkably consistent story. Ilmenite materials migrated to the near side and sank into the interior in sheet-like cascades, leaving behind a vestige that causes anomalies in the moon's gravity field, as seen by GRAIL. The researchers' observations also constrain the timing of this event. The linear gravity anomalies are interrupted by the largest and oldest impact basins on the near side, and therefore must have formed earlier. Based on these cross-cutting relationships, the author suggests the ilmenite-rich layer sank prior to 4.22 billion years ago, making it consistent with contributing to later volcanism seen in the lunar surface. Analyzing these variations in the moon's gravity field allows us to peek under the moon's surface and see what lies beneath," Dr. Bouquet said. And while the detection of lunar gravity anomalies provides evidence for the sinking of a dense layer in the moon's interior and a more precise estimate of how and when this occurred, the researchers say that what we see on the surface of the moon adds even more intrigue to the story. The moon is fundamentally lopsided in every respect, Dr. Andrew Hanna said. The researchers explained the near side facing the Earth, particularly the dark Oceanus Procellarum region, is lower in elevation, has a thinner crust, is largely covered in lava flows, and has high concentrations of typically rare elements like titanium and thorium, whereas the far sides differ in each of these respects. Somehow, the overturn of the lunar mantle is thought to be related to the unique structure and history of the near side Procellarium region, though the details that overturn have been a matter of considerable debate among scientists. Dr. Andrew Hanna said, "For the first time, we have physical evidence showing us what was happening on the moon's interior during this critical stage in its evolution, and that's really exciting. It turns out that the moon's earliest history is written below the surface, and it just took the right combination of models and data to unveil that story. The vestiges of early lunar evolution are present below the crust today, which is mesmerizing. Future missions, such as with a seismic network, would allow a better investigation of the geometry of these structures." Mr. Lang added that research such as this could assist astronauts in upcoming manned missions to the moon, saying, "When the Artemis astronauts eventually land on the moon to begin a new era of human exploration, we will have a very different understanding of our neighbor than we did when the Apollo astronauts first set foot on it." And this is on Express UK by James Gamble. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.